today we will have lecture of Professor Lakhotia, who knows microscopy in this university probably the best. He is the person who opens the microscope any kind of problem. In our department, after Corona, many of the microscopes were in such a state as if they cannot be used. It is he and Dr. Richa R. They cleaned all those microscopes and they are now better than the condition they were. So that is the kind of person Professor Lakhotia is. You will learn from him. Please welcome Professor S.C. Lakhotia.
All right, I'm happy to be talking about microscopy. And I believe that some of you might have heard it, so it may be a kind of rehearsing the same thing all over, but still something may be learned, something may be better understood. Microscopy is what I'm going to talk about is just the basics, not the confocal aspect, but except that I will introduce you why confocal and how does confocal work, how does it differ from a regular microscope. This picture that I really like is what drawn in 1665 by somebody who had kind of made microscopes. I mean, those days they used to make microscopes themselves, Leeuwenhoek and Robert Hooke. And what one really needs to appreciate is not only the detail that one can see, but also the art that goes with it, hand drawn, not photographs. And actually photographs cannot match the hand drawing, and that's something that I will emphasize again and again, that in the process of automation, in the process of modern techniques and the high-end techniques, we are often losing some part of our brain, the activity that we can do otherwise. And this is one remarkable example that just see the beauty of the whole drawing. This is eye of an insect, the compound eye, and one can see each of these rounded circles are the individual eyes that make up this compound eye, and this is what it is. Now, let's say, why do we need, doesn't move, why do we need microscope? What we see with eyes has a limitation in the sense that how small an object we can see. And our eyes can see only about 0.1 millimeter, not more than that. That's the smallest dimension that we can see. And therefore, if objects which are smaller than that, we need to see with light microscope. And objects which are still smaller, we need other kinds of microscope, for example, electron microscopy, which in theory, electron microscope can even possibly look at individual atoms, although that has not so far been achieved, but in theory that's possible. So basically we are talking about this range, which is between about 1 millimeter to 0.2 micron. That's the range that we use the light microscope for. And why do we do that? This is not working. Okay. We need microscope to see smaller objects, and microscope provides two important functions. One is magnification, that is high image size to object ratio. That's an important function, that the object is small, but its image that we generate is larger than that, and that's what we call magnification. And the ratio between the image size and the object size is what we call it the degree of magnification, how much magnified it is. 1x is same size, 2x means twice, and so on and so forth. But an important function that microscope does is what we call as resolution. And that is what is the smallest size of the object that can be resolved to be a separate entity from a neighboring object. What's the minimum distance between two objects that must be there to distinctly see them? That's what we call as limit of resolution, or the minimal distance that we call it. I'll explain that. And the typical highest resolution that we can get with optical or confocal microscopes are 200 nanometer. That's standard. The super resolution confocal microscope, they claim that they can get up to 50 to 120 micrometer. Nanometer. Whereas electron microscope can go to less than 0.1 nanometer, and so on. So that's where the But electromagnetic needs a different preparatory technique, confocal needs a different one, and standard optical microscope again needs a series of different preparatory techniques that we make use of it. And so microscope based on visible light spectrum can then be used to see objects smaller than 200 nanometer. I mean, cannot be used below this. That's where we need to go to other modes of microscopy. In addition to electron microscopy, there are a variety of what is known as tunneling microscope, which like atomic force microscope and so on, which work on different principles. I'll not be going in detail about that. And a typical microscope that we use today has a much more of electronic regulation, mechanical regulation, and multiple functions. For example, a typical bright field microscope will also be combined with a fluorescence microscope. That's the kind of standard configuration that we have. And the fluorescence microscope component, is this part, which generates very strong white light with the entire spectrum from UV light to infrared, and then we can select which wavelength we want to excite. But the standard bright field microscopy component is light source is here, and it passes through a series of filters and lenses, and at the bottom there is a reflecting lens which diverts the light straight to the optical system. And below this stage, this is an upright microscope, you have the condenser system. Unfortunately, condenser system we often ignore. We just say it's to take light, but that's the most essential and critical component of microscopy to decide how good your image will be. And that requires adjustment of the condenser properly. Every time you use a microscope, this has to be adjusted. Every objective you change, you need to adjust this. And that's where a number of regulation controls are there. For example, this is for moving the condenser up and down to focus the lights, the lights that's coming in onto the object. And then there is an iris diaphragm here, there is an iris diaphragm within this condenser, and there are centering screws which will make the light to be centered, and this must be done. Once this is all done, light passes through the object, through the objective, and then can be made to go to the visual system through a binocular, monocular head, or to a camera detection system, which can be the classical film-based camera, or can be a video camera, can be a digital camera, whatever camera system you want to have. And the fluorescence microscope, I'll come to this later on again. The whole thing follows the optic principles to generate a magnified inverted image typically. But now, of course, the systems are different, that we can get a real image which can be projected, no more virtual, and which can be straight image as well because of the using the kind of prisms that are here. So that's what a bright field microscopy is. Based on this, there are a variety of modifications that have happened to enhance the contrast. For normal bright field microscope, we need to stain the object because they are otherwise very transparent, the refractive index is not very high, so we can't see distinctly. So there are a number of enhancing techniques. One is staining. Depending on what you want to, what kind of stain you use, certain parts of cells are visible, tissues are visible, others are not, and you get different colors. But more others are that where you want to examine a live cell, then staining is not possible because staining will kill this cell. So for live cell imaging, there are a number of contrast enhancing methods, which can be polarizing microscopy, which can be phase contrast microscopy, or differential interference contrast microscopy. Okay, but before I go to that, let me explain the difference between resolution and magnification. These are images of polyethylene chromosomes from Drosophila, which is one of my favorite material just for its beauty and the advantage that it offers. What you can see that this is a field taken with a 10x objective, which has a numerical aperture of 0.3. I'll explain this numerical aperture later on again. Then the same field, if we look at with a 20x objective, we will not see the whole of it, we will see only part of it, because the field of view becomes smaller and it has a numerical aperture of 0.5. If you go to a 40x objective, again the field of view becomes smaller, objects become slightly larger, and we can see better details which you can't see here. And that's what we mean by resolution. That resolution, magnification is improving, resolution is improving. If you go to 100x all objective, we still see more details. Of finer details that we can't just make out here, they are here. This is because it provides a higher magnification. I'm sorry, this should be 100x, not 1000x. This is a mistake here. and its numerical aperture is 1.3. Now, to differentiate between or to understand what magnification versus resolution is, let's look at these images. These are same chromosome magnified to same level. Magnification is same. But this image is taken with a 10x objective. This is with 20x objective, 40x objective, and 100x objective. Now you can see the difference between magnification and resolution. They are magnified to same level. But this doesn't give you any resolution. Actually, you lose what information you had in the smaller image than when you magnify it. When this is very simple, that our skin is made of cells. If we take a very sharp picture of our face, shall we see cells by keeping on magnifying it? It will become like this ultimately. You won't see anything. You won't even recognize your face. So that's where one has to understand the difference between resolution and magnification. Resolution means what is the minimum distance objects that you can resolve clearly and separately. And that's what increases. The limit becomes smaller as we increase the numerical aperture. And this is what we calculate by this formula that was given by Rayleigh more than, I think it was almost 150 years ago that this was decided, that the numerical aperture depends on this delta x is the minimal distance between two objects. For example, in this case, the distance between these two, what should be the minimal distance? That's delta x, which has to be a constant 0.061, which is a constant. Lambda is the light, wavelength of the light in which you are imaging, and n is the refractive index of the medium through which light is passing. In case of glass, when you use glass and cover slip, it's 1.5 numerical, the refractive index. Then there is an angle called sine theta, sine value of a theta angle. Theta angle is defined by the objective's numerical aperture. If we can approximate this also by lambda by twice Na, because 0.61 if we take it 0.5, then it becomes lambda by twice Na, because this value n sine theta is equal to numerical aperture of a lens. And so it can be simply stated as lambda by twice Na. For example, if you are using a wavelength of 500 nanometer, and if your numerical aperture is 1, then you can calculate, you will have 250 nanometer resolution. That's an approximate calculation that one can make. Now, how do we explain this in terms of real optics? This was again a physicist, Airy, had defined what we call as Airy disk. And the idea that if from a circular hole light passes through a very small pinhole, it will undergo refraction at the edges. And therefore, the image of that circular hole will look something like a bright spot, but then rings of less and less intensity surrounding it. Although the opening is circular, but these Airy disks happen because of the property of the optical property of light refraction. Now, what resolution tells us is if there are two pinholes through which light is passing, then if the distance between these two pinholes is such that these main Airy disks are not overlapping, we can resolve them. But if they are very close, they are overlapping, we will not be able to say that they are two separate objects. And this is what defines the limit of resolution. That what's the minimum distance that must be there between two objects, in this case pinholes, but in other case microscopy it can be cell structure or whatever you want to see, minimum distance between them so that their Airy disks are not overlapping. And so what happens is, depending upon the numerical aperture of the lens, this angle is what we call a theta angle. So if the numerical aperture is larger, the theta angle is larger. And so you have the different numerical apertures, and correspondingly, the Airy disk size is larger with smaller numerical aperture, with the smaller angle theta, but larger when the angle theta is smaller, and smaller when the angle theta is larger. And therefore, the resolution that you get becomes smaller, because again ultimately Na is refractive index multiplied by the sine theta value. So sine theta value of this will be more than that of this. and consequently the denominator being larger than numerator, your minimum distance becomes smaller. That's the thing that you should know. When we say it has a better limit of resolution, means it can differentiate objects which are smaller distance separating them. So there's a reciprocal relationship between limit of resolution and the distance. Smaller the distance, we say better the resolution. Okay, and that's what we calculate by this. And this is where in objective, when we are using, you see the objectives are made of different classes and categories, and they will have, they may be same magnification, but they may have different numerical aperture. And accordingly, their optical quality that they produce the image will vary. And therefore, one must understand that what kind of objective we are using. Immersion objectives are those where we use a liquid between the objective lens and your object. They can be water immersion, glycerol immersion, or oil immersion. Water immersion gives less resolution than glycerol, then oil, because the refractive index of these media keeps on increasing. Oil is very good because oil refractive index that we use in microscope, not the standard hair oil or cooking oil. These are microscope immersion oil made specifically for this. Their refractive index is 1.5. They are non-evaporating, and therefore they are used between the objective lens and the slide or cover slip so that light doesn't have to refract again. It can go and you can get this optimal refractive index and the numerical aperture value. All right, now these are the different ways that I was mentioning about contrast inhibition. For example, this is a mitotic metaphase. Same metaphase looked in direct microscope without any staining. You see a faint image because these regions are denser, therefore they have more refractive index and therefore they become separate from the cytoplasm as such. If you dark field microscopy works on that direct rays of light do not enter the objective. It's only refracted rays that will enter, and they can be, I'm sorry, this is polarized, sorry, not dark field. Polarized, that means light waves which are oscillating only in one plane. When we say, typically when we say light is traveling in this direction, light as a whole is traveling in this direction, but individual waves in which direction they are oscillating, because each light wave has to oscillate in this. And there's 360 degrees or more, depending on how fine you take the angle, they can oscillate in different degrees. And standard normal light that we see is unpolarized. Polarized light means that all the waves that are comprising a given beam of light are oscillating in one particular plane. If they are oscillating this way, then all of them are oscillating this. If this, all of them are in this plane. And that's what we call polarized light. And if you look in polarized light, then depending upon the component that make up a structure in this cell, light will behave differently. And so mitotic spindle, which has microtubules arranged in a linear order, will appear in one particular direction of polarized light completely dark. If you change the polarized light, this may appear much bright and chromosomes may appear dark. So this is one purpose that polarized light does. Then there is another system, differential interference contrast. More popular is the phase contrast, which each of them makes use of certain properties of light wave when they are oscillating in which direction and what direction you are calculating. But this has become more popular, especially with confocal microscopy, because in confocal microscopy or fluorescent microscopy, we use fluorescent stain which will let you see the object in a bright field like this. But if you are combining with DIC, then you can look at the cell structure also. And so when you use confocal imaging, always use DIC along with it. All confocal microscopes are equipped that you can combine a differential interference contrast optical system along with your confocal imaging or fluorescence imaging. This, of course, is with electron microscope, not of course the same cell, but similar stage. And this is a hand drawing, which is what one will interpret the structure to be. But these are different ways, and of course, if they are stained, then this will look colored. All these imaging systems give you monochrome images, no color. Neither electron microscope, nor phase contrast, nor DIC or polarized. They are just monochrome, black and white. We can give them pseudo color if we want to, but typically what the image that we get are monochrome images. Then fluorescence lies at the root of confocal microscope. And this phenomenon was discovered in 1800s by George Stokes using a fluorspar, one of the minerals. And the phenomenon is that fluorescent light is emitted only during absorption of excitation light. And the fluorescent light that comes out has a longer wavelength than the light that is falling on it. Now, what we should understand this is, each of us is wearing a colored dress, all right, different colors. Light is white. Are we seeing these colors because of fluorescence? Because I said fluorescence will give you a different color. So are the dress of our colors of our dress because of fluorescence phenomenon or what? What it is? Why do we see these different colors? Anyone? Why do we see the different colors in different dress? Somebody is blue, somebody is black, somebody is red, light is white. Why do we see the different colors?
Due to absorption of some amount of some color of light and reflection of
Right. Some wavelengths, because what we see color is because of wavelength. And the white light has a spectrum right from, for a visible spectrum that we can see, let's say we can see about 450 to 650 nanometers is our range approximately. And between that we make out different colors from blue to or ultraviolet to or violet to red. And so what happens is when white light falls on this, then depending upon the constitution of the dress or whatever it is, some wavelengths are absorbed, others only are reflected. So when we say red dress, that means only the red wavelength is reflected, others are absorbed. But in fluorescence, something different happens. It's not because of differential absorption, but here it happens because of the phenomenon of excitation of an electron and its reversal back to the ground state, and in that it gives out energy which is less than the original energy. See, that's what we say, that a typical structure of an electron is that you have a proton and these electrons in different orbits. And each, for an atom to be at a stable state, all electrons and protons must be in the proper orbit. Because if an electron changes its orbit, the molecule is in an unstable state. So, for example, if some particular wavelength of light energy falls on this electron and it acquires more energy, then it jumps to outer orbit. Now, this is an unstable state, or we call excited state. If this on its own comes back, it must give out that energy, and that energy is given out as light, but some amount as heat, and therefore the light that comes out has a longer wavelength, because energy of each wave depends on its wavelength. So if let's say X amount of light was absorbed by this electron to come to outer orbit, it goes back, it must give out X amount of energy back. But if X minus some value goes at heat, then for light the energy becomes less, and therefore that light becomes longer wavelength. And this is what we see in fluorescence, that it's an instantaneous process, because this excited state lasts for an extremely short period. It comes back immediately, and immediately the light that was coming, falling on it of a shorter wavelength, light that comes out is of a longer wavelength. And that's typical fluorescence. It's instantaneous process. But to be able to see this, we should be able to remove the excitation wavelength. Because if excitation wavelength is there, then we will not see the fluorescent wavelength, because that's much smaller in component. To understand this point, let's just ask, on a clear day, why don't we see stars? They don't disappear. They are there, but why are we not able to see them?
sunlight is more powerful.
Because the surrounding light is so bright that dim light our eyes can't detect. But in night, of course not in city now, we have too much of light in the day, but you go to a darker place, then you can see all these stars, because now there's no more sunlight. So it's a question of relative intensity. So if the emission light is very small compared to the excitation beam, we won't see this. So we need to have something that will cut off the excitation beam path. So we use a filter, and that's what we call as a barrier filter, which will remove wavelengths of a certain size and allow wavelengths of a certain size, so that we can see the excitation. And this is what we do in a fluorescence microscope. What we do here is that, for example, if we have something that is excited with blue light and emits green light as fluorescent. Then we pass on through a filter blue light only. So this filter is excitation filter, which from the white light remove all but only allow blue light to pass through. Then blue light falls on the object, which has the property of fluorescence, and when blue light falls on it, it emits green light. Now, but then both blue and green both are traveling together. This filter that we call barrier filter will have to remove the blue light and permit only green light. And so this is what lies at the heart of fluorescence microscope. Okay, this is, for example, if we come back to the same image but now we explain fluorescence, what we are doing here is the mercury lamp, which is typically used in most fluorescence microscopes, gives very strong source of light, white light, ranging from ultraviolet to infrared. So it has the entire spectrum. So this white light comes here, and here we have an excitation filter. So depending upon which wavelength we want to fall on the object, for example, if we want blue, we would use a blue excitation filter. If we want green, we will use a green excitation filter. If we want a red wavelength to excite, we use red excitation filter. So different filters are available. Then this light comes to in the center here, there's a dichroic lens or dichroic mirror. Dichroic mirror has the property that in one direction when light falls, it is reflecting. In another direction when light goes, it's transparent. That's the property of a dichroic mirror or dichroic lens. And so what happens here is this light that comes in this direction, it reflects light down to the objective on the object. If the object has a fluorescent material which gets excited with green light, it will emit, let's say, red light. Now, but both green and red light will travel back through total internal reflection, and that's what we are going to use for imaging. Now, here you have green as well as red. What we now need is, we need another filter that will cut off the green, allow only red to pass through. So that's how this construction is, that we have one side the excitation filter, on the other side the emission filter, and in between a dichroic lens. So together when they are put in the optical path of the fluorescence microscope, you see the fluorescent image. Because now what happens is the fluorescent image is complete dark, because the whole field is illuminated, let's say, with green light, but that green light is no more coming to your eyes. Only red is coming. So only the parts of the cell or tissue where you had a molecule that will get excited with green light and emit red light, they will be visible. Rest will be all dark. And that's what fluorescence microscopy does for. The important point here is that these filters can be of different categories. What part of spectrum they will allow. There are filters that allow different parts of spectrum, and we have one is what wide band pass filter. That means it will allow from this wavelength to this wavelength all the waves to pass through. We can have a narrow band filter which allows only a very small part. So depending upon what kind of object you are looking at, what kind of fluorescence you are expecting, and what wavelength you want, one can choose. Typically one would prefer for precision a narrow band pass filter. But there are other band pass filters which are called short pass or long pass. That means for example, this SP filter will allow any wavelength lower than this to pass through it. Pass, on the other hand, will not allow any wavelength smaller than this, but will allow all, and these are used in confocal microscopy, depending on which kind of fluorochrome we are using and what kind of imaging we want to take. So one can use these combinations of wide band pass, narrow band pass, or short pass or long pass filters. And the details are provided with each filter, that what is the spectrum that they will allow and how much they will allow at each point. That can be understood very clearly. Now, this is what a confocal microscope would be. This was, of course, a historical microscope that happened to be the first multiphoton confocal microscope in India that we had in our lab. In I think 2000 it was installed, but then shortly it had to be given up because the company stopped supporting it, and so then we went for a different microscope in 2007, and this microscope is what is working with us since 2007, almost non-stop. Of course, again, this model is no more supported by JICE. They stopped supporting this 2000, so they have newer model. But fortunately for us, this is still working. What this confocal microscope involves is one part that is not shown here on this side will be source of lasers. Instead of mercury lamp, for confocal we need lasers because we need much more intense light. And that's what lasers provide, a particular wavelength and very intense light. So there is a source of lasers from which light will come through an optic fiber on the back of this microscope, and through which they will be directed through the objective, and then image goes, and this part is what we call a scan head, which will generate the confocal imaging. Different models have different kind of system, but basically each one of them will have a source of laser, a basic microscope, a good quality microscope, which will have both fluorescence and visible light as standard. But in addition, we'll have a scan head, confocal scan head. There are different kinds of confocal systems, and they will have different scan heads, and it will be all computer controlled. There's software and a high-end computer that is required to generate the data, collect the data, and control everything in the microscope. It can have a standard camera as well to collect the images, but confocal images are not collected by this. They are collected by the photosensitive system, photomultiplier tubes or spectral detectors or whatever it is. They are built in the scan head. I'll try to explain the anatomy of this part later on. Now, when do we need it? What's the problem with fluorescence and confocal? What's the difference? Confocal microscope works on principle of fluorescence. So something that we can see with fluorescence only we can see with confocal. So why do we need a confocal? The problem in fluorescence microscope is a tissue thickness is there. A certain thickness is there. Your tissue may be even 10 micrometer thick, it's 10 micrometer thick. And what happens is, coming from the top layer, if you are focusing on that, all the fluorescent light coming from other layers are out of focus. Can you please turn it off? Okay. So because of this out of focus light coming from different layers than the layer that you are focusing on, total image looks blurred. For example, here in this tissue we have two fluorochromes, one giving you yellowish fluorescence, another giving you green fluorescence, but the image that you get is all blurred. The same thing if you look in confocal, same tissue, you see all the details. Now how does confocal do this? We are not cutting sections of the tissue. We are still keeping the total tissue intact, but we get sharp image of a particular plane. And that's what we'll see, that how does it happen. Now in a fluorescence microscope, we have, let's say, we put a pinhole here so that only a small area is illuminated for fluorescent light. But light is coming out from all these layers, tissue thicknesses. Our objective is focused at this layer. So from this point, the fluorescent light comes out a sharp that is in the center. So this again, you may recall, I don't know how many of you would have done this experiment of using a pinhole camera. Anyone did it? You have learned about pinhole camera? That if you have a dark room and close no light on one window, put a cardboard and a single hole in it, and you will see on the other wall a projection of what is outside. That's pinhole camera. Why does it do it? Because if you recall the image formation system, the focus light is always in the center of the point of focus. The light that are not in focus at the focal point are outside that central point. And so the image from the focal point will be in the center, but image from other layers which are not focused will lie in the periphery. But in a typical fluorescence microscope, all these rays are reaching your eyes or to the detection system, and therefore embedded in that out of focus image is also a focus image, but you can't make out that. What confocal microscope does is a very simple principle. The same thing here, what I showed you earlier, it just introduces this additional component, another pinhole here. Rest everything is same as in fluorescence microscope. Just one more pinhole is added, which is at same point, focusing at same point where this pinhole is focusing, and that's why we call it confocal. that two pinholes are focusing at same point. That's confocality, or they're confocal. But because of this pinhole, what happens is all these out of focus light rays are prevented from entering our eyes or from your detection system. Only the sharp images go in, and consequently, same thing, if you didn't have this pinhole, will give you image like this. The moment you introduce pinhole, you get an image like this. Is that clear? Any point on this part before I move further? Is it all right? Now, but this introduces one problem. A problem is that we are seeing at particular time on just one point of the tissue, not the entire field of view, because you are illuminating it with an extremely small point, and the image from that one small point only is coming to your eyes or to detection system. Our eyes or brains, one limitation is that we can't keep on remembering what we saw even a fraction of a second earlier. When the next image comes, our brain has lost the continuity of the previous image. And therefore, if we say, all right, I'll keep on imaging each point separately and look through the eyes, we don't see anything. We can't see, because all that we can see is just one point. And that point is so small that our eyes will not actually be able to detect. So we need a detection system that can detect this, but then we need a system which can collect images from all the three axes. And that's we talk of scanning confocal microscope, that it must scan the entire area in XY direction and in Z direction. And so the laser scanning confocal microscopy is the laser beam of depending wavelengths that you want, depending on fluorochrome, will illuminate one particular part of the specimen, and then it excites all of the, but at the same time it's exciting all the points in that Z-axis, but the image is collected only from one particular Z-axis. Z-axis is the thickness part. X, Y are the horizontal part, and Z-axis is the thickness part. So in thickness, we are focusing at one particular point. From that point only, the fluorescent light is detected. And therefore, and that light is detected, by a photomultiplier tube or some other detection system. What it must do the capacity, and that's where computer comes in, software comes in, that it will record point by point intensity or the wavelength and intensity of at that particular pixel, keep it recorded, move to the next, and so basically it then scans x-axis, then y-axis. So on x-axis it will scan all the points. Move one step towards y-axis, scan all the points. Move towards another y-axis point, scan all of them. Once this entire area is covered, it will move in z-axis by a determined step that you decide, whether it should move down by 0.2 micrometer or 0.3 or 1 micrometer or whatever it is, depending on the kind of microscope, the kind of information that you want, and then repeat the same XY scanning. That's why it's called a scanning confocal microscope. So that's what it says, that once all the pixels and axes are collected, the laser beam shifts to the next y-axis pixel, scan all axis points on that, and after completing this, it moves to the z-axis and does that. And what PMT sends its signal to the computer, and computer software stores all the point information and then can generate that image that you begin to see. And that's what it is, that you at one point you are getting image only of a particular point. From light source, one point is illuminated because of the pinholes, and that point image only is collected. And that's where you need the scanning component of it. Now, there is the pinhole, what function it has. Actually, confocal microscope depends entirely on the pinhole, what size of pinhole you are using. And this is, for example, an experimental demonstration that if you use pinhole which is equal to 1 area unit, that means the limit of resolution of that microsystem. We get, let's say this is the Drosophila eye, developing eye system, and we have this green one that the axons, and the red is something that we are seeing, two components. The same system partly magnified here, and you can see details. If you are using pinhole, which is absolutely equal to the limit of resolution of 1 area unit. If we open it up more, if this pinhole size is more, you get brighter image. But then you are losing the focus and the details. Open it more, your image gets much brighter, but that's like a standard fluorescent microscope now. And this is what determines that, yes, how good image you will get, how good is the imaging capability of the microscope, the photodetector system, how sensitive they are, what laser power you are using, and all that will determine the quality of the image that you get. But sometimes you see, everybody wants to, okay, I should have bright image. You are losing all the details. This looks very bright, but then details that you see here are all gone. We don't want this, because if we want this, then I don't need a confocal. I will go straight to fluorescence microscope. For getting confocal, we must make sure that our confocality is appropriate. The pinhole sizes and the laser powers and the detection system, all these digital imaging parameters that come in must be properly adjusted. And this is what happens in a scan head. This, of course, is a very simplified drawing. Different modelers will have different kinds of arrangement, but basically what's happening is, these are, let's say, the sources of laser. We can have 2 lasers, we can have 3 lasers, we can have 4 lasers. Each one will give a particular wavelength, and we can select which laser light will come. So there are a series of these filter wheels. Some filters function as dichroics, some filters function as excitation filter or barrier filter. So depending upon, for example, if I were to take light from this laser, then I use a filter that will direct all the light down here. If I use this laser, again I use a filter that will direct all the light down here, and in this filter I use a plane transmission, no reflection, no absorption. And then that is again reflected back through a collimator here, which will adjust for all the laser waves to be focused at same point, because different wavelengths will have different focal points. So that must be adjusted so that all of them focus through the objective on the object. Then you have fluorescent light being generated that travels back, and then depending upon, these are, for example, photomultiplier tube that are light sensitive. Each one can be used for detecting a particular wavelength of the fluorescent light, or you can have a spectral detector where you can identify each part of the spectrum to be detected by, for example, this has actually 32 detectors. So you can define detector 1 to 5 will collect this wavelength, detector 6 to 10 will collect this wavelength, so that you can identify. But then whether light will go to which one, you can control these different filter wheels. The software allows you to identify which filter wheel to use for which kind of barrier filter, which kind of excitation filter, or a dichroic for reflection. And accordingly, you can decide that light generated on this particular wavelength will go to this photomultiplier tube. A fluorescence generator, for example, this blue one will go to this, red will go to this. That can be determined using the software. And the scan head has a mechanical system that will immediately and in a very fast way. It can't take time. It must be absolutely time that you can't detect. Fractions of a second, it must move these filters to right position and send the light to the given direction. And this will be combined with this scanning system. That again requires a mechanical system, that the stage moves in a particular direction or the pinhole moves in a particular direction. So depending on the different microscope, either the stage moves, or in most cases, it's a pinhole that is made to move. Both the pinholes, in the excitation path and the detection path, both pinholes must move simultaneously. And that's what makes the cost of the microscope, because this requires very precision, not only the optics, mechanical components, and the software component, which will regulate the whole thing. Now, one of the points that we must be careful about the property of fluorescence is bleeding through. Each fluorochrome has a spectrum in which it can get excited and a spectrum in which it will give its wavelength, the fluorescent wavelength, to allow it to pass through. There is a peak excitation. For example, here what we can see here in this drawing on the lower part, that a particular fluorochrome has this emission spectrum. Okay, its excitation spectrum will be somewhat on this side, lower than this. But it's not just one particular wavelength, that point where it gets excited. It may get excited, let's say, for example, from 390 to 450, anywhere. But it will have a peak excitation. Similarly, emission, it can emit wavelength from here to here, but peak emission is here. So what we want is that when we want excitation, we use the peak excitation path to pass. The laser should be close to the peak excitation point. And our filter system that we use in the detection side should be close to the peak emission side. But sometimes its excitation can be, its emission part can also be exciting for the next fluorochrome. Because very often we use 2 or 3 fluorochromes. And for example, one fluorochrome, we have used this and it gives an excitation between, let's say, 480 to 620, it gives excitation. We collect at, let's say, at about 490. But the light is coming out. In the same cell or same tissue, another fluorochrome, which needs 550 to this excitation wavelength. So what happens is this emission wavelength also excites this. And therefore, that's what we call bleed through. And this is what's happening here, that for example, one fluorochrome gives this image, but if we do simultaneous detection, that we excite both the fluorochromes, which is possible in confocal, that you can excite both the fluorochromes together and detect both of them in 2 PMTs. But then some of this excitation beam will excite the next fluorochrome also. And therefore, you get a combined image like this. But if you do a sequential, that you first detect the image with only green, next you detect only with the red emission, then you get this image. Now, unless you have taken care, you may come out with this interpretation that the molecules are localized everywhere together, which they may not be. And so this must be taken clear, that when you combine 2 different fluorochromes, their emission and excitation spectra must be, may not be completely non-overlapping, but should be largely non-overlapping. But if they are overlapping for some reason that you can't get a fluorochrome of a certain kind, then you must do serial scanning. And you must also record how much it will generate fluorescence because of the other fluorochrome. And then software allows you to minus that from the particular fluorochrome intensity. So this is something that we must understand, that each fluorochrome, although we say, okay, I'll collect this image at 488 nanometer excitation, and the filter will collect peak at 540. But its excitation again has a range. What you are trying to collect is close to the peak of the excitation or peak of the emission spectrum. That's what we are trying to do. And so this must be for each fluorochrome. The details are available. The spectra are available, that what's the emission spectrum, what's the excitation spectrum, and that must be carefully understood to decide which fluorochromes we can use together. And if we do it fairly well, this is a very classical picture of Drosophila embryo, that see, in Drosophila the embryogenesis happened that initially there is only nuclear division, no cells are formed. But already at that stage, each nucleus has a different gene expression pattern. And this is what determined that these cells know that they are anterior and these cells know that they are posterior, the nuclei, and this is what can be detected through a confocal microscope using a number of fluorochromes together and detecting each one of them image carefully and then putting them together. That's what is the advantage of doing this. And these kinds of images have been really instructive in letting us know what happens in development, how cells get to know, but also in any tissue, which cells are expressing which kind of protein or which kind of RNA. We can use techniques like in situ hybridization to detect RNA, or immunostaining to detect proteins or something else. And so that one can combine RNA and protein together, or RNA and DNA together, or protein and DNA together, or some other molecule, lipids or something, as long as you have fluorochromes or antibody that will identify a given class of molecule. They can be combined together. This is another, for example, Drosophila. This part is the brain part, larval brain hemisphere. This is the equivalent to our ventral nerve cord, and this is the developing eye. This will be the developing antenna, and one can see more details, which tissue is how forming, which proteins are localized where, and so this is where the beauty of confocal microscope is. That's something that we cannot see with normal imaging system, normal microscopy, bright field microscopy, or even fluorescent microscopy. You see, if I were to look at this with a typical fluorescent microscope, I can stain both red and green, but then I won't be able to distinguish individual, because out of focus images will blur the real image, and that's the advantage of confocal microscopy that comes in. This is a classical picture that was collected in our lab by one of our former students, Dr. Anand Tiwari, who is now at Gandhinagar, developing iDisk, he took about 90 optical sections. What you mean by optical section is that each layer of z-axis that you say, we call it an optical axis. XY scan in one dimension is one optical section. You move to the next, you move to the next, and this way that the previous one that I showed you, this iDisk, this part took so many images by letting the focus objective move at different focal pace. And then what software can do is, it can combine all the images together. And then you can rotate it. Now you don't need the tissue at all. Your image is all software based. And you can rotate and you can see individual structure. Now, in individual image, this is not clear at all. You can't make it out. But once you combine, because digitally what has happened is, each point in each frame is a fixed point, and that the software knows. And it can superimpose each one of them together and generate this image. And you can make out how these green ones are the kind of axons from the photoreceptor cells, and you can see how these optic nerve, it goes and projects on the brain. And this is something very remarkable. I'm sorry, I realized that the movie that is there, that you can even rotate this image, look from under or over or from any side, will not function somehow in the system, so I deleted that. But that's something that can be done. And it's really not only aesthetically pleasing, but information-wise, tissue architecture-wise, it provides remarkable information. And that's the beauty of confocal microscope. And now, of course, the microscopy system, the imaging system has gone much better. And so we can, like the system here is supposed to give you much better super resolution besides standard confocal. And that's the advantage of these systems is. This is, for example, another thing that you can look at live. So this is what was Anand Singh had done this when he was doing his PhD, that these structures, I'm sorry, that one can make out that they are, okay, I think it stopped moving now. Whatever region it was. Okay, that these, in live cell, how these molecules move. If the molecules are tagged with GAP, a particular molecule is tagged with GAP or RFP, one of the, which can express in a live cell and which is fluorescent, then we can look at them in a real situation. All we need to do is time-lapse imaging. So we add a fourth dimension. X, Y, Z is a spatial, and then we add a temporal dimension. 1 second, 2 seconds, or a fraction of a second later, what happens, and that can be done. This is another thing that we can do. Again, I'm sorry, I deleted the movie because it was not working in my system for some reasons. I thought there's no point in wasting time. But this is again live imaging, that certain molecules will move if cell is stressed, or they are all here and they get concentrated here. And one can take time imaging 1 second, 2 seconds, 3 seconds later after heat shock, and then one can see that all of them move to one particular place. And this can be now seen as a movie also, how actually things happen. Because you can combine time with it. You can actually have a time going on for a day, 2 days, depending upon what your microscopy system allows you to keep your tissue, your cells alive. Cells in culture can be placed on a confocal microscope, and you can have some fluorescent components there, and you can trace them for a day or 2 days. But of course, that microscope will need that. On this stage, you need maintain proper temperature, proper humidity, proper CO2 concentration. That means you need a tissue culture chamber on the microscope stage itself. And then one can do that kind of analysis. Or this thing when the cells recover, how from this one particular point, its molecules come out every second. And you see, this gives one impression. Things in cells are really not as slow as we are slow. The cell can respond within 1 minute that temperature has gone up outside. We don't realize, but cells can, and that's something that we can record by using live imaging system. Or there are now softwares available. For example, this is, again, this was done by Anand, that RNA polymerase on polyethylene cones or wherever it is. This is a fluorescent microscope, normal fluorescent microscope. But software-wise, ImageJ provides this kind of software plugins. You can get images like confocals, good super resolution confocal images. You don't need a super resolution confocal microscope. Although this may not be as accurate as a hardware super resolution will provide it, but it's nearly same kind of information one can get using appropriate software that have been developed now. So one can actually see that each dot perhaps represents one RNA polymerase molecule. That's how they are there and where they are there, and one can follow them. If this RNA polymerase was tagged with a GAP, then we can actually see it moving in a confocal microscope if you have the appropriate system. But I'll come to the last part. Having talked about these advanced microscopy, I always like showing these nearly 120-year-old pictures, hand-drawn, beautifully colored, and the detail that they show, I don't think our current microscope will show it. What your eyes can see in microscope, by changing the focus and changing the contrast and so on and so forth, the optical system, no matter how good they are, they'll not show you all the details. Another one, a microscope like this generated these drawings. The first description of mitosis by Fleming in 1882. Using a microscope like this. With a confocal microscope like this, we show metaphase cell division like this. You can decide which one gives you more information. Now, one can then argue, why do we need a confocal microscope if we can do this? But yes, we need, because it doesn't tell you which molecule is where. It only shows you structure, provided you have the patience to sit down, focus, change focus, and keep on drawing everything. These are again hand drawing, not photographs. Looking at thousands and thousands of, Fleming's book is available online. And you can see in that book, there are hundreds and hundreds of hand drawings of chromosomes, how do they look like, and so on and so forth. And that's really remarkable that if you have the patience, if you have your keen sense of observation, you can see more details, then automated system will do it. But that doesn't mean that confocal microscope doesn't give you, but don't lose your brain in your thinking while using confocal microscope. Or any modern gadget that we use, we must do this. And that's what I will say, that the automated and increasingly powerful equipment and tools available for cell biological studies allow precise in-depth analysis, yes, but we must not forsake our own analytical insights. What we see, then it's up to our brain, our thinking, our analysis to interpret what it is, to understand what it is, and that must be kept intact. So with that, I'll close and take any questions. But you see, one pinhole is only, what it is doing is exciting on that point along the entire depth. And that's what creates a blurriness. So we need to eliminate out of focus images. And therefore we need a second pinhole. The only case where we don't need a pinhole is when we use multiphoton system. So in multiphoton system, what happens is that we excite the object with a longer wavelength. Okay, not the excitation wavelength. For example, if my fluorochrome needs 450 nanometer excitation, I'll excite it with a 900 nanometer wavelength. But if that laser is pulsing, that means it generates a laser, goes down, again generates, again goes down, and if the interval between two pulses is less than 100 femtosecond, then what happens is, same electron, if it receives two photons simultaneously within an interval of 100 femtosecond, it will move to the higher orbit. Okay. Then in that case, what happens is, wherever that happens, only that point will give fluorescence, rest will not give. Now, where is the highest probability of two photons hitting same electron? Think of it. One simple answer I'll give you is, if any of you have tried to burn a piece of cotton using a magnifying lens with sunlight. Any of you have done this? Now, does it burn wherever you put magnifying lens? Magnifying lens must be focusing. What do we mean by focusing? More of sunlight energy is at one particular point, and that's at the point of focus. And same thing we do in multiphoton, that at the point of focus, the probability of two photons hitting same electron is the highest. So rest of the depth, you have less energy and therefore less chance of fluorescence. Only from one point fluorescence is coming, and that's the point of focus. So in this case, you don't need the second pinhole. That's the only case in multiphoton. And that's one advantage of multiphoton is that you are exposing tissue to lesser energy because you are using higher wavelength and the photo damage is less. But then one problem that can happen is because of infrared it can otherwise get heated, but prolonged exposure can quench fluorescence at other levels as well. So there are the trade-offs. What you can do with multiphoton, certain things in better than in standard confocal and vice versa.
So what is the correlation between pinhole and air unit?
See, pinhole, that means the size of the pinhole, for example, if your 1.4 NA numerical aperture object lens gives you a limit of resolution of 200 nanometer. If your pinhole is 400 nanometer, then you are not collecting image only from the point of focus. You are collecting the peripheral out of focus rays as well. And so total light intensity that you receive becomes more, your image looks brighter, but you are losing the limit of resolution. See if I can, let me go back. Yeah. If you look at this, now if your pinhole is larger, then these two objects, their air units will tend to, because out of focus light from different planes will tend to merge and you lose that resolution. So one area unit is defined as the limit of resolution. So for different objective lenses, it will vary. And this software provides that how much pinhole you want. It has an option. You want 1 area unit, 1.5 area unit, and accordingly it will adjust the opening of the pinhole.
So if we decrease the pinhole less than 1 area unit,
You are not gaining any, you are only losing information.
just no resolution change.
Because actually your image will become less bright because you are giving less light, and that's not good. Ideal is 1 area unit, but if your fluorescence is very less, you can compromise either by increasing laser power or increasing the digital gain or by increasing the pinhole a little more. But then the moment you open the pinhole more than that, you are losing some resolution, spatial resolution. Any other question?
Sir, actually the bleed through you explained, right? Actually, I just wanted to know the simultaneous, sequential and serial. I think you said...
Well, simultaneous and serial. Simultaneous means that you can direct your confocal microscope to use two lasers together and record each one image in separate channels. That's simultaneous. Serial is you record one channel, it turns off. I mean, laser doesn't turn off, but the light from that laser is off, and you start another and repeat the same thing at same setting. So that's serial. That you examine one color, one fluorochrome, then you examine second fluorochrome. Simultaneous, you are examining both the fluorochromes together. But if you want to do simultaneous, then you must make sure that there is no bleed through. Even in serial, one has to ensure that there is no bleed through. But that will be much less, which can be done. But in simultaneous, if they have an overlap of excitation and emission spectra, you can't stop it.
So, for that we have to design, I mean, the experimentation in a such a...
Yes, you need to use your fluorochromes, antibodies or tagged with fluorochrome, which are non-overlapping excitation and emission, or minimally overlapping. Because what happens is that the excitation the spectrum is like this. So even if this overlap, but the energy is so less that it may not excite the other fluorochrome at that level, because it needs a certain minimal amount of energy. And so because the spectrum is always has a long tail which has very low energy and a peak center part. So as long as these are very distinct and the overlap is only in the very weak energy component, then it can be used. But one has to make sure that you run appropriate controls to make sure that at that power your other fluorochrome is not excited. How many of you have used regular microscope or fluorescence microscope? Most of you have used. Some of you have not used. Or, I mean, is it that some of you have not used a fluorescence microscope? Yes or no? Anybody who has not used? All right. So, I presume each of you have used. Then it's much easier to follow what a confocal microscope does. Confocal looks very great, but all that it does is simple. 2 pinholes, focus the same point, and eliminate out of focus images. That's all. But rest is all. We don't need to worry about what computer does, what software does, but we should know what it is doing, so that then we can control things in a better way. We can decide what speed we want to examine, what area we want to examine, what resolution we want to examine. You can take same image, same area with 540 by 540 pixel, or 1024 by 1020, I mean 512 by 512, or you can split that same area in 1012 by 1012 or 2024. Higher the pixel, better resolution, but longer time. And then you have to worry about whether your fluorescence will be quenched by the time it starts from this end and goes to the other end, because it's getting exposed. So this has to be done with experience and with understanding what it involves. Because no fluorochrome has eternal life. It will quench its fluorescence. I mean, in a simple way, it just gets tired of getting excited and coming back, and refuses to get excited at some point. That's what we call as quenching. Of course, quenching is a factor because of heat, because of generation of reactive oxygen species, so that the molecules undergo conformation change and therefore they don't excite anymore. But this is something that we need to understand. Different fluorochromes have different degrees of quenching. Some tend to quench very fast, some can take a little longer time. So with experience, you can select which one to do and under what conditions you want to scan it. All right, thank you then. I'll